9.4 Weather Processes. Atmospheric pressure and circulation. Atmospheric pressure is also called barometric pressure, which is the weight of a column of air above a given point. Or another way to say it, it is the force exerted by molecules on the surface. In the atmosphere, pressure decreases with increasing altitude. This vertical change in pressure is due to the fact that nearly all of the weight of the atmosphere is in the lower atmosphere. If you don't believe me, look at the graph and listen to your ears pop next time you go up in elevation. On the x-axis, we have pressure in millibars. On the y-axis, we have distance above the Earth's surface in miles and kilometers, with the different levels of the atmosphere labeled for reference. So, based on the graph, where does it look like we are super close to 0 millibars? Your eyes may be more refined than mine, but to me it looks like we've approached really close to 0 millibars in the middle of the stratosphere. What is the pressure at the top of the troposphere? My eyes say about 200 millibars. Do you approximately agree with my eyes? At the Earth's surface, we are at about 1013.2 millibars. So yep, most of the atmospheric pressure is in the troposphere. Makes sense because that's where most of the atmospheric molecules are, which also makes sense because of gravity. Atmospheric pressure and circulation. So there are horizontal changes in pressure too. Changes in air temperature and air movement are responsible for horizontal changes in pressure. Temperature influences pressure because cold air is more dense and exerts greater pressure on surface, and there are global variations in temperature that cause global winds. At the equator, air is warm and low in density. This creates low pressure zones at the equator, so air rises, condenses, forms clouds, and rain. Their air also cools due to its higher elevation in the atmosphere. The cooler, drier air sinks at latitudes around 30 degrees, causing deserts. We'll discuss. Here is an image of the major circulation cells, as well as the lows and highs. Let's start at the equator. The equator is hot. The sun's rays hit the most directly near the equator, lots of energy. The hot earth warms the overlying air. The warm air picks up moisture because it can. It has enough energy to evaporate water from the earth's surface. The warm, moist air becomes less dense than the air around it because it is both warm and moist. Why? For warm, think of why a hot air balloon rises. For moist, we need to think about molecular weights. Here is a handy periodic table to help us with molecular weights. Okay, what is most of our atmosphere composed of? Did you say nitrogen and oxygen? I hope so. Okay, nitrogen and oxygen both like to hang out in pairs, so as N2 and O2. Now the molecular weight of nitrogen is about 14 atomic mass units. So the molecular weight of the N2 molecule would be 14 plus 14, which equals 28. The molecular weight of elemental oxygen is about 16. So the molecular weight of the O2 molecule is 16 plus 16, which is 32. Now, what is the molecular weight of water? Water is composed of 2 hydrogens and 1 oxygen. The molecular weight of elemental hydrogen is about 1, and oxygen is 16. So water's molecular weight is 1 plus 1 plus 16, which equals 18. Now, which molecule is lightest? N2, O2, or water? Right, water, by a lot. So when you add water to air, the air for a given volume or parcel actually becomes lighter. And so back to our circulation cells. Warm, moist air rises at the equator. As it rises, it cools. Why? I bet you thought something like temperature decreases with an increase in altitude in the troposphere. And we know what happens when moist air, too moist air, as it cools, the humidity increases and will probably become saturated. So condensation and cloud formation and rain. Have you been to the equator? Near the equator? Someplace warm and humid like Florida or the Carolinas in the summer? What was the typical weather pattern? Often what happens is that through the morning and early afternoon, the sun warms the earth, which warms the air, which evaporates water and becomes moisture and less dense. The warm, moist air is barely breathable, and you wish that something would make the weather cooler, like perhaps some rain? Well, your wish is often the weather's command in this situation, and in the later afternoon to early evening, the warm, moist air has risen high enough to cool a bit and achieve 100% relative humidity, form clouds, often cumulonimbus clouds, big, tall thunderhead clouds, and let go with a brief and violent thunderstorm. That's the equatorial low for you when you are at the equator. The low refers to low pressure. Because the warm, moist air is rising, there is a less pressure on the surface of the earth. Now let's follow the air poleward. It is cool up at the top of the Hadley cell. And as the air travels away from the equator, it loses more moisture and becomes cooler too. Cool, dry air is more dense, and so will fall back to the surface of the earth near the Tropic of Cancer in the northern hemisphere and near the Tropic of Capricorn in the southern hemisphere. As the air mass falls back down to earth, the dense air pushing down causes the subtropical high, as in high pressure. Also, the cool, dry air begins to heat up a bit as it decreases its altitude. Now, as this cool, dry, warmish air is thirsty, its humidity is undersaturated. It can evaporate more water, and it does, creating those deserts as mentioned earlier. Here's a map with the world's large deserts. Now there is more to weather patterns than just the circulation cells, so the deserts aren't perfectly lined up with the 30-degree latitudes, but they are around the 30-degree latitudes. Do you agree? If not, you can probably agree that there are not extensive deserts around the equatorial low. Yes? More weather processes and atmospheric circulation. Air movement can cause changes in pressure. Convergence occurs when air flows in, increasing pressure, and divergence occurs when air flows out, decreasing pressure. The cartoon below depicts the convergence and divergence aloft and the resulting high and low pressures at the surface. So remember, the air is just like pretty much everything else. It moves away from areas of high pressure to areas of low pressure. And remember that warm, moist air is less dense and rises so that there is a low pressure. And cold, dry air is more dense and so it sinks, creating high pressure. Let's impersonate these different air masses. First, act like warm, moist air. Rise up. Create low pressure on your chair. Come on, rise up. Low pressure, warm, moist air. Perhaps stretch out like you're hot and trying to dry some sweat off you. Whatever helps you remember. You are warm, you are moist, you rise, you create low pressure. Okay, now impersonate cold, dry air. Sink down. Increase that pressure on your chair. Huddle up like you are cold. You are cold, you are dry, you sink, you create high pressure. Okay, now back to the cartoon. Convergence increases pressure aloft, so air moves away from the convergence. Some of the air moves down towards the surface. The air is coming from aloft, so it is colder and drier than the air at the surface, creating a high pressure and an anticyclonic flow as air continues to move away from the high pressure. Divergence, it decreases pressure aloft. This lower pressure causes air to flow towards it, sucking some warmer, moister air from near the surface upwards. This causes a low pressure at the surface and cyclonic flow. Here is another cartoon that is a bit simpler. It highlights that convergence of air aloft corresponds to sinking or subsiding air. And high pressure, both at the surface and aloft, and divergence aloft corresponds to rising air. And low pressure, again, both at the surface and aloft.